Well, hi again, this is Bob, and I'm looking at the bottom of page 293 now. This is the third of four new distributions, although some of them are going to look a lot like things we've seen before. And this one's called the hypergeometric distribution. And again, I'm assuming that you've read through this, but this time they're telling us that when sampling's done without replacement, you may recall that's different than the binomial distribution. It tells us the binomial distribution does not give us exact probabilities since the trials are not independent. Okay, that goes back a couple of places. The smaller the size of the population, the less accurate the binomial probabilities will be. And then they give us an example here. They say, suppose a committee of 4 people is to be selected from 7 women and 5 men. What's the probability that the committee will consist of 3 women and 1 man? Okay, well, the idea for this particular question, just imagine that we've got these 12 people and we're going to pull out 4 of them for a committee, and there won't be replacement. This is a different situation of what we've seen before. And we've, in that sense, but we've seen questions like this before in Chapter 5 previously. And for this particular question, recall that there are 7 women and 5 men. This should look familiar. And the total number for the committee, we're going to have a committee of 4. And the breakdown from the 7 women, we're going to choose 3. And of course, that would only leave 1 for the committee man. Okay? So there's a lot of ways you can organize this in a table, but the total number of ways that this could be done should make sense that from the for the total number of ways to make the committee. This is like the fundamental counting principle, K1 times K2. Here would be the number of ways, 7 combination 3, to choose 3 women from 7, and this gets multiplied times 5 combination 1 for the men. Now, recall that we don't care the order that the committee members are actually chosen. That's why we're using a combination instead of a permutation. And they tell us, and this would be very easy to tap into your calculator, that this can happen 175 ways. Okay, there's 175 ways to choose 3 women from 7 and 1 man from 5 to form the committee of 4. And of course, notice that the 7 and 5 add up to 12, and the 3 and the 1 add up to 4. Okay, that might be helpful. And again, we've seen this before. When we figure out, we already know that our numerator is 7 combination 3 times 5 combination 1. Look at what they get on the denominator there on the top of the next page, which is 294. They get 12 combination 4. Okay? That's the total number of ways that you can choose 4 people, in this case, from 12. And if we just go back a page here, as I mentioned, notice that this 7 and this 5 add to 12, and this 3 and this 1 add to 4. Okay, so we can, if we have the numerator, we can always come up with a denominator. Oops, I hope I didn't lost a page there. Well, no wonder I can't go back. So anyway, I thought I'd already written this, but here's what we've got. For our answer to the question, for this individual probability of X, I think I lost a page there. we had the 7 combination 3 times 5 combination 1, and then in the denominator we had 12 combination 4. And what I was trying to point out, and this will always be true, that the first number, the number we're choosing from for our combinations, will always add up to that first number in our denominator. And of course, the second number of the combinations, the number of people we're actually choosing from the women and men, will always add up to the total number selected, in this case for the given committee. So, to solve this particular problem, recall that the numerator turned out to be 175, and the denominator was 495. 12 combination 4 is 495. All right, and they gave an answer as a fraction, but normally I would give it as a decimal. The answer turned out to be 35/99, which is about, you know, it's pretty close to a third, or around 33%. We're always interested in the answer, but what's important here is that we understand where these numbers came from and how this relates to how the numerator relates to the denominator and vice versa. Anyway, let's look at their definition, and if this seems familiar, it's because we've already done this a little earlier in this same chapter here. How about the conditions under which we can use the hypergeometric distribution, if you will? And they tell us that the variable only has 2 outcomes, and sampling is done without replacement, as like when we saw this committee question here. And again, there must be a fixed number of trials. In this case, we had 12, or from the 12, we're choosing 4. There are only 2 outcomes. You're a man or a woman. And for the committee in this case, success or failure. The sample is selected without replacement. Okay, so just imagine 7 women and 5 men, maybe, you know, sitting down at a long table or standing up in front of a class of some sort, and we just start picking people out. Replacement is not done, and as we've also seen, we have 2 outcomes. In this case, you're going to be on the committee or not, and that's determined by the number of men and women chosen. Anyway, let's look at the formula, excuse me. And if you noticed, we've got our NCX, that's, in that case, would be like for the women, and then you have, I'm sorry, they're using an A here. I'll use their terminology. In fact, I think what I'm going to do is I'm going to put the question that we just did there a second ago, our setup, okay? And again, here's the formula for this hypergeometric distribution here. It's ACX, capital X, times B to N minus X. No, for shoot. I can say it, but I can't seem to write it. I'm just crossing my fingers again that I don't lose my connection here. Because it looks like there's all kinds of stuff happening when we write the formula out. But if we can relate the formula to the example that we just did, notice that the ACX, in this case, this was like our women, and this would be like our men for the committee. And the first thing we noticed that there were a total of 7 women from which we chose 4 and 5 men from which we chose 1. Well, notice that this would be the A and this would be the B, And of course, 7 plus 5 would equal the 12 in our denominator. Okay? So if we had if there were 12 people we were choosing from, and 7 of those were women, then 12 minus that, the number that we chose. In other words, excuse me. What I'm trying to say here is the 12 minus the 7 gives us 5. We're going to have a total of 12 people, and there's so many different ways you can explain this. Actually, I was trying to find the B there. Okay, so in this case, they would tell us that there were 7 women and there were 5 men that we were going to choose also. So the 7 is given to us and the 5 is given to us. Okay, and 7 and 5 in the denominator are going to make 12. Now, how do we get the second number, the total number we're choosing? That just turns out to be the number of women we chose first, which was 4, and then the total number that we are going to choose, which was 5. So this just becomes 5 minus 4, or 1. And I know that's really a big mess there because I've written over myself. So it's easier for me to explain it this way. The top 2 numbers that lead, in other words, the 7 and the 5, should always add to the total number that we're choosing from. Okay, so that's the breakdown. 7 women, 5 men, that adds up to 12. Okay, and the number, the respective number, remember it's a binomial type situation. From the 7 women, we're choosing 4, and from the 5 men, we're choosing 1. That 4 and 1 in this case will add up to the total number selected for the committee. Okay, since it gets so wordy, I just thought I would carefully do 2 questions here, or at least set up the 2 questions. One of them is one of your homework questions, but I thought I would do example 531. That's at the toward the bottom of page 294. And this would be the perfect type of question to demonstrate that formula that they give us. Of course, the formula looks more involved than it is. You've got 10 people apply for a job as assistant manager of a restaurant. 5 have had completed college, 5 not. So if we have something like, lost my pen there, 5 college, and then 5 not completed college. So our total number that we're choosing from right away we can see is 10. So the manager, 5 college, 5 not, the manager is going to select 3 applicants from the 10 and wants to find the we want to find the probability that all 3 are college graduates. Well, our 5 college and 5 not college would be like our binomial situation here. So if we were to select from the 5 with college, the 3, remember the manager is going to select 3 candidates or 3 people from the 10, and all 3 of them are supposed to have college. Okay, so that would, I'll put a 3 here, meaning that of the 5 at college, we wanted all 3 of them, the applicants chosen. So what does that leave for the ways to pull out the other applicants? Well, that would leave 0. because we're only choosing 3, and if all 3 of them have college, then that leaves 0 that we would be pulling out that would be not college. In other words, we're not breaking it down by 2 college and 1 some college. It's just all 3 college. And if it makes sense that at the bottom we would have 10 combination 3, that's good, because notice that the 5 and the 5 add up to our total of 10, and our 3 and our 0 add up to the number selected, 3. Okay? And remember also that 5 combination 0 is just 1. So this basically turns out to be 5 combination 3 over 10 combination 3. And the book tells us that this is about 0.083. So there's about a 1% chance, if you will, or excuse me, about an 8% chance of the 3 applicants chosen, of all 3 applicants chosen having college. Okay, well, I thought I would close this one off. And again, I just again want to stress, you can always make sure that the problem is set up right, or should be set up right, if you're too, in this case it was a number breakdown of college and not college, add up to the total number chosen, and then you're choosing from that total number a certain number. In this case it was 3, and notice that 3 and 0 add up to the number chosen. In this case it's 3. So I thought I would close off by setting up your one of your homework problems, which is 19. And that's on page 299. It's another job application problem. And it tells us you got 12 people apply for a teaching position in math at a local college. 6 have a PhD and 6 have masters. Okay, so 12 people total. 6 have a PhD. 6 have a master's. Okay, well, let's see how many are chosen. If the department chairperson selects 3 applicants at random to interview, find the probability that all 3 have PhDs. Okay. Okay, so the first thing I would do when I normally set these things up is I know we're going to choose 3 to interview from 12, so I know my denominator right away is 12 combination 3. That's a big help, okay? Now, from the, notice that we're going to select 3 people, and each of the 3 people have a PhD, and there were a total of 6 PhDs and 6 masters, so it should make sense that when we're talking about the PhDs, that we're going to choose all 3, we're choosing 3 candidates to interview, and we want all 3 of them to have a PhD, and we're choosing from 6 that have a PhD. I'm just sorry that it's so wordy, but this is one that you can verify in your solution manual also. Well, what does that leave for the other combination there? Well, we had 6 people with a master's, but we're not interested. We've already used up the 3 that are chosen, so that would be 6 combination 3 times 6 combination 0 over 12 combination 3. And to verify this, I noticed that 6 and 6 add up to the 12. That's the total number that could be interviewed, or total number of candidates, and that we've taken care of the 3 to be interviewed by the fact that all 3 of them are going to have a PhD, and that would leave none of the interview for just a master's. Okay, So this would just break down, because 6 combination is 1, that would break down to 6 combination 3 over 12. I lost my pen. 12 combination 3. And the solution manual tells us that comes out to be about 0.0909. Or around 10% if you like. We normally leave the answers as decimals. Okay, well, that's the idea, and if it seems familiar, it's because we did do something like this earlier, and I think that's a good place to stop. We don't need to build on that anymore. From example 531, which I worked out, and from homework question number 19, which we set up and worked out, that should be enough for you to have exposure to the hypergeometric distribution, and you should be able to do a question like that on the test or a quiz. And of course, recall on tests, I always write a extremely close practice test and provide a key. Okay, I will be back shortly with a new distribution or new formula to our text. It's called the geometric distribution. Thank you.